All right, let's take a look at how we can actually use this double angle formula business to actually start solving even more exotic trig equations. I know that's what you live for, solving these trig equations. Suppose we want to solve this one. Cosine 2x equals sine x. And I only want to find the solutions for x inside of 0 to 2 pi. So that means I just want the angles between 0 and 2 pi and nothing else. Well, you see, this one is a little bit annoying. Your first instinct may be to divide by the cosine, so I get sine over cosine, which is tangent. But see, they're not the same angle now. So sine x divided by cosine 2x is not tangent of anything. It's just a big mess. So this is actually pretty scary. How would you handle this? Well, now we're armed with a formula for double angles for cosine. So I can actually take the cosine 2x and convert it into just cosines and sines of x's and stuff. So let's do that. So using the double angle formula for cosine, I see this actually equals cosine squared x minus sine squared x. And now that equals, by this thing, sine x. Well, now we're in pretty good shape because now everything is just x's. There's no 2x's here. I'm a little bit troubled and disturbed by the fact that this is a cosine stuff and everything else seems to be sine. I would love everything to be uniform, either sine or cosine. Well, I can't change that to cosine. That seems almost impossible. Could I change this to sines? Well, yes, because now I remember the fundamental Pythagorean identity, which is equivalent to saying that sine squared x plus cosine squared x equals 1. So what does cosine equal? Well, if I bring this term over to this side, I see that cosine squared x equals 1 minus sine squared x. So in place of cosine here, I can replace it by 1 minus sine squared. So let's do that. So if I do that, I now see, in place of this, I write 1 minus sine squared x. And don't forget that term, minus sine squared x. And that still equals sine x. So notice that now everything just has x's, no 2x's, and everything is a sign. So in fact, that's a good sign. All right. Now you may think these cancel out, but be careful they don't, because I have a minus sine squared and a minus sine squared. That's minus 2 sine squared. So in fact, those square terms remain. Let's bring everything over to this side. So I'll bring the minus 2 sine squared x to this side. It becomes just plus 2 sine squared x. So I have a plus 2 sine squared x. I have that term, sine x. I'm bringing everything over to this side. And I bring that over. I see a minus 1. And what does that equal? Well, that will equal 0. Well, now what you might want to do is just call this something in order not to confuse the issue, because I'm going to try to factor now. Or you may just begin to start to think about the something as sort of at the same time as actually factoring. So I'm going to put a sine x here and a sine x here. I'll put the 2 here. So that product is 2 sine squared x. Now I want the terms to multiply at the end to give 1, so I'll put in a 1 and a 1. And the signs should be opposite. But how should I put them in so that when I do this inside and outside, I get a plus 1? Well, I think if I put a plus sign here and a minus sign here, that's going to work well. Because here I see a plus 2 sine x minus a sine x gives me a plus sine x. So in fact, this actually works out great. So I factored this in one fell swoop. And so what does that mean? Well, it means that now what I can do is set up 2 equations. One is that this thing equals 0, and the other is that this equals 0. So let's just rewrite that up here. So I see 2 sine x minus 1 times sine x plus 1 equals 0. So that's where I'm left with now. So either this equals 0. If 2 sine x minus 1 equals 0, that means that sine of x must equal 1/2, right? Because I'd bring this over to the other side as a plus 1 and divide both sides by 2, so I'd see this. Or the other possibility is that this equals 0, which means sine x equals minus 1. Well, now we have to find the solutions. And remember, we're only looking for solutions between 0 and 2 pi. So you can't look outside. You have to look only inside here. Well, minus 1 is an easy one. There's only one answer. It equals minus 1 right here at 3 pi over 2. So that's easy. Here, x equals 3 pi over 2. Now what about this one? Well, this one's a teeny bit more work, but not too much more work. At a half, it crosses the half here, but also here. So there's going to be two answers to this one, and they're going to be both symmetric to this thing. So whatever I have here, I'll take pi minus that here. And what's the answer here? Well, sine of what angle is a half? Well, I happen to know that's actually going to be 30 degrees, or pi over 6 radians. So I see that x equals pi over 6 radians. That's this answer right here. Gives me a half. And how do I get the one that's sort of symmetric on this side? Well, I take this length, which is pi over 6, and subtract it from pi. I move off that much this way. So I take pi, and I subtract pi over 6. And pi is actually 6 pi over 6. That's just pi. But minus pi over 6 gives me 5 pi over 6. So the other answer is x equals 5 pi over 6. So this equation actually has three solutions. X equals pi over 6, x equals 5 pi over 6, and x equals 3 pi over 2. Those are all solutions to this original question where the x is bound in this region. So notice what I did. I had this thing, it had cosines and sines, but more fatal, it had a 2x and an x. So I got rid of that by using the double angle formula. Then I didn't like the cosine, so I got rid of that using a Pythagorean theorem formula. And then I set up this nice thing, which turned out to be just a factorable quadratic. This had two solutions, this had one solution, and they're all the solutions in that range. Okay, great. So you can actually solve these kind of exotic equations now using the double angle formula.